So it's an order of operations issue where if we knew what x was, then we'd have, if x was 7, we'd say 7 minus 5, and then we would square root. So the subtraction would happen first, right? So kind of inside-ish. Then the function would happen. So the function here is the square root. Whereas if we said x was 7, then we'd have to figure out what the square root of 7 was first, then the subtraction happens. So we're saying the subtraction would be outside of the function. So this inside versus outside stuff is about when the math happens. So when the math happens before the function, again, the function here is the square rooting. That's defined as being inside. If it happens after the function, then it's defined as being outside. Okay? Or it can be kind of a more visual thing where we can see that it's under the radical versus not being under the radical. Okay? So inside versus outside. So what I'm going to do is when we flip back and forth between Desmos to show you guys what the graphs look like. I'll sketch some of them for you guys, and we'll talk about patterns and things we're seeing. Again, most of the stuff should be pretty familiar to you. So look at each of these functions here. So starting off with absolute value. So the absolute value function, of course, is that v with its vertex being there at the 0, 0 at the origin. Okay, so then if we wanted to say what's the absolute value of x plus 2, so we'll add a 2 in there. So oops, there's a 0. So what is that? What happens there, right? So we see that the was at 0, 0 is now at negative 2, 0. So all the points have shifted to the left 2. Then it wanted x squared. So of course x squared is our parabola. And I wanted to say x minus 3 squared. So I need to put some parentheses around this. X minus 3, close my parentheses. So what happens there? All right, so we see that vertex that was at 0, 0 now has been shifted to the right 3 points. So that one shifted to the right 3. And then the other one was the square root. So that's this one. All right, so there you see that it starts at 0, 0, only goes to the right, curve to the right. So if I wanted to say the square root of x minus 1, what happens there? So we see that little starting point, right? What was at 0, 0 is now shifted to the right 1. And so all of the other points are also shifted to the right 1 unit. Okay. So kind of just paying attention there that these are shifts left and shifts right. So this was a shift left 2 units. And what we saw graphically was that the vertex was supposed to be at 0, 0, but instead it was over here at negative 2, 0. And that was a v. So something like that. Now this one was a shift right 3 units. And what we saw graphically, so what's supposed to start at 0, 0 should be a parabola. Instead of starting at 0, 0, start over here at 3, 0. Did that. And then this one we saw was a shift right 1 unit. And so that one should have started at 0, 0, but instead it started at 1, 0. And that graph, that square root graph, is essentially it's half of a parabola. So if we drew a parabola that was sideways, okay, that's only the top half that we actually see. So it looks something kind of like that. It's a pretty flat curve. I kind of accentuated that one a little bit, but it should look something like that. We're going to look at some more functions, different transformations on them though. So I'm going to go back to Desmos. Oops. So at the cube root, The 1/3 power is the same as a cube root, so that's what I've seen there. We want that plus 2. So what happens there? So notice the cube root is a stretched out s, goes to the right and left. Right, again, very flat curve. What happens here? So that point that was at 0, 0, so that kind of center point of the graph has been shifted up 2 units, right? And everything else has been shifted up 2 units. Look at the rational function, the reciprocal function. Some of you guys that were in Algebra 2 last year would have missed out on this. This was COVIDed. So what we see here is that there is, it's called a hyperbola. There's the 2 branches of the hyperbola, the 2 pieces of the hyperbola. And that each axis is what's called an asymptote. It's that vertical asymptote there at the y-axis and the vertical asymptote there, or horizontal asymptote at the x-axis. Notice how the graph does not touch those axes, right? It gets closer and closer and closer, but it will never touch them, okay? Well, I want to take that and I want to subtract 3 from it, so minus 3. So it's a little hard to see what's happening here. Let me grab this. So here what I've done, I put in the line y equals negative 3, that horizontal line through negative 3. We can see that that is now the asymptote, the horizontal asymptote. The vertical asymptote is still the y-axis, but now this line y equals negative 3 is my new horizontal asymptote. So it had been the x-axis, but putting that minus 3 there on the function shifted it down 3 units. Okay? So we don't have a center to this graph, like there's no point at the center because it doesn't touch that, but we can use those asymptotes as kind of helping us see where things have shifted. So, and the last one was x cubed, which is this guy. So x cubed is a vertical s, again, very stretched out vertical s. The right side goes up, the left side goes down. And then I want to subtract 1 from it. Let's see what that looks like. And so that point that did run through 0, 0 now has shifted down 1 unit. Okay, and then it curves up and curves down from there. Okay. So you see that all those adding, subtractings outside of the function are causing up and down shifts. So here we had a shift up 2 units. So that graph started at 2, 0, or sorry, 0, 2. And again, a pretty flat curve off to the right, up, down to the left. Should look like a really stretched out S for the cube root. The 1 over x minus 3, that was a shift down 3 units. So sketching that was the hyperbola, has the asymptotes, is really kind of its defining feature. So if you think about that vertical asymptote, which is at x equals 0, that one didn't move. But the horizontal one, the y, moved down through. So if we draw a line down here, it's y equals negative 3. So as we try to draw that on that top right corner, we start pretty close to that vertical asymptote on this side. Curve. Make sure you're curving. Don't do this. Don't make an angle. It's a curve. Curve down towards the other asymptote. Don't touch it though. And in the bottom left corner, we do the same thing. So the graph should look like that. And then this last one, let's shift down 1 unit. So x cubed was a vertical S. So here at 0, -1. So okay, try it again. A little too straight up. Kind of like that. So what do we need to watch out for with the left and right shifts? Inside lysos. Yeah. Sounds like Maddie remembers something I used to say a lot. Yeah, so you can't trust that sign, right? It says +2, that's actually a left shift. It says -3, that's actually a right shift. Okay. So the sign is going to lie to you here. It's going to, don't trust the sign. Okay, so and you guys that were with me last year might remember you saying H is a liar. What that comes down to is that with these problems, there's like a form to them, which looks something like this, where we'd say y equals a times x minus h squared plus k, or and this one would be y equals a times the square root of x minus h plus k. And I always said that h was a liar, but we knew that if it says plus, that's actually a left shift, and if it says minus, that's a right shift. With the up and downs, we trusted that one, but just knew the inside was going to lie to us. So yeah, I would definitely watch out for that. All right, so mostly what you guys are going to be doing today is going to be, it's multiple choice stuff for a lot of the graphing. You're not graphing by hand, which is lucky for you. I would definitely be making you do that by hand if you were here. So how do you do multiple choice with this stuff? Okay. First thing you need to do identify is what's the function. Okay. So if we're looking at a square, what should the graph look like? If we're looking at a square, what should the graph look like?
A parabola.
A parabola, yes. Okay. So if there were any graphs that weren't parabolas, you could definitely eliminate those right off the bat. Okay. So, okay. And then what does the +1 do? What does the -2 do? So what's happening to this parabola that we have? What's the +1 do? What's the -2 do? I need to be more specific than that, Victoria. Like, what is the shift? Is it what direction? How much? Stuff like that. So we are talking about shifts, but what direction? How much? So it's not right 2 units, no.
Down 2.
Okay, so we have a down 2. Okay, what about the +1? Left 1? Okay. Okay. So how do we, pick out that graph? Okay. So we definitely should be looking for a graph of a parabola. Anything that wasn't a parabola can definitely be chucked out. Right? If you got 4 choices, right? Anything that's not shifted left and down, right? So if there's definitely going to be a graph that's shifted to the right, boom, it's out of there. Right? There definitely would be a graph that would be shifted up, boom, it's out of there. Okay. Maybe there's 2 that are shifted left and down. So you got to make sure they're, which one's which. What if they shifted it left 2 and down 1? Right? It'd be a pretty easy switch to make. Okay. So how do you make sure what should you be looking for? So if it was supposed to start here, right, there's where our vertex is supposed to be. I go left 1 and then down 2, it should be starting about here, wherever -1, -2 would be for you. Okay? So something like and then the graph should be a parabola from there. Okay? You get rid of any that aren't parabolas, you get rid of any that aren't shifted left or down, right? And you should be probably down to at least 50-50 by that point. If not, there's only one left. Okay. What about this function? What's the graph look like? This one does not have a name. What does the graph look like? Should be looking at earlier today. Should be looking back at your toolkit functions. Okay, half a parabola. Need a little bit more than that, Maddie. How way does it go?
Isn't it like a half of a parabola, like sideways, just going off in one direction?
Which way?
To the right.
To the right and
Up.
and up. Okay. So we need a half a parabola off to the right and up. Starts at 0, 0. Curves off to the right. Up. Okay. Horizontal S is the cube root. So this is kind of just half of that, right? Cube root would be the other, both directions. Square roots only go one direction because remember we can't square root mid roots. So there should be no values on that side of the y-axis. Okay, so so anything that's not that shape should be gone. What's the -3 do? What's the +2 do? What's the -3 do? What's +2 do? Shift 3 right. That's good. Okay, what else? Up 2 units. Okay. So as we go to think about what that would look like, we could easily eliminate anything that doesn't go up, right? So more specifically, making sure that goes into the right amount. So 3 units right, 2 units up, so that'd be again. Show up something like that. Okay. Anything you guys want to talk about with up, down, left, right? I'm going to summarize that a little bit. So where it's what the operation is, where it's adding, subtracting, and also where it is. Okay. So adding inside the function, graph, shifts, left. And then adding outside. Okay. Graph shifts up. Essentially, you can write in the same sentences, but subtracting. Subtracting inside, the graph shifts right. And subtracting outside. Graph will shift down. Anything shifting wise you guys want to talk about? Okay. All right. So I'm going to go to what's called vertical stretching and compressing. So look at these functions on Desmos. Go back to x squared. So again, x squared, of course, is our parabola. So it's our parent function. So what if I wanted to have 2x squared? Right. 2 times x squared. What's that look like? So you should notice that the vertex didn't move, right? But now the graph appears to be narrower than in the past. Right? Look at square root. So there's our parent function. Now I want to do 4 times the square root of x. Right? So what's that look like? There we see quite a bit of a bigger curve here. And then the last one was the cube. So x cubed. Okay. And what does 3 times x cubed look like? So again, what I describe that as is a narrower. Notice that it's the red part is closer to the y-axis than the black part there. Okay. On both the top and the bottom, it's pushed in towards the y-axis. So I call that to be narrow. Okay. So what these are all called are vertical stretches. So this is a vertical stretch, and we need to say by a factor of, and how much. So it's a vertical stretch by a factor of 2, and there are no words here that you can leave out. They're all necessary. So we are going to talk about horizontal stretches, so we need to notice which way it's stretching. Okay? And then there's vertical compressions. So we also need to say it's a stretch, not compressed. And we need to say by a factor of, because when we talk about factors, those are things that multiply. So we need to make sure that we're using that word to imply that the 2 is multiplying the x squared. It's not adding to the x squared, which we saw, can cause a shift. So all of those words are necessary to talk about that transformation correctly. So what did that look like? So we saw with the parent function that started at 0, 0. That's a parabola, or something like that. I'll just read the word x squared. This is much more like comparative to me. Right? I said it looks narrower. If I don't have something to say it's narrower than, then I can't. That word kind of loses its meaning. Okay, so then 2x squared would be something like that. So this one appears narrow. Okay, so it's a vertical stretch, but it appears to be narrower to our eyes. And mathematically, I'm going to show you guys how this is happening. The y value is being stretched. And so if we go back and look at this real quick. So what I'm going to do is I'm going to look at a particular point on x squared. If I plug in 2, right? If I plug in 2, I get 4. That's my answer. Right? 2, 4 would be a point on the parent one. Well, if I plug in 2 into the other one, it was 2 times x squared. So x squared being 4, and then 2 times that would be 8. So the other red function, the transform function, the same x value would give me a y value of 8. So why is it called a vertical stretch? So what's happening here is that notice that the distance from the x-axis, the green point, is 4 units. The distance from the x-axis to the purple point is 8 units. Okay? So the distance is 2 times larger for the purple point than it is for the green point. That's what we're saying, that the y values are being stretched away from the x-axis. Okay? That's why and so what's happening here is those y values are growing even faster than they were before, right? This already grew pretty fast, right? You look at the sides of the graph, it's mainly going up. It's not really going to the side much. Now they're growing even faster. So since they're growing so fast, they don't have as much time to expand visually for us. That's just what I think. They don't have as much time to expand visually, and so they only look skinny. Okay? That's the way it works for these vertical-looking graphs, right? Again, a parabola grows up very quickly. It's the same thing with a cube. Cubes grow up very rapidly, right? And down. It's mainly going up and down. It's not going to the side much. And so when I multiply it by something, it just gets skinnier because it grows even faster. Okay? So these vertical graphs just look narrower when we stretch. Versus a graph that mainly goes left and right. If we look at a square root, that graph mainly just moves to the right. It doesn't move up and down much. Okay? When I stretch it, it actually looks stretched. Right? It looks taller. Okay? So something weird happens, right? Versus those vertical graphs versus the horizontal graphs. How they react to this thing visually for us. And the math is all the same. But our eyes kind of read them differently. So if we think about a point that's easy to square root, like 9. Okay? So if I plugged in the x value of 9 into the square root, I'll get 3 back as my answer. Okay, so there we see that 0.93 on that graph. Well, the other one is 4 times that. So I'm going to plug in 9 again. Square root of 9 is 3, times 4 is 12. And so there's that 0.912 on the other graph. Right? So again, what we're looking at here is the distance between that point and the x-axis. So for the green point, it's 3 units. For the purple point, it's 12 units. So that distance is 4 times more for the purple point than it was for the green point. That's where we're seeing that y value being stretched out. Okay, that's why the graphs act like that mathematically. We've got to deal with the fact of how they look visually. This can be tricky. So here for the second one, this would be a vertical stretch. by a factor of 4. I am going to sketch this one. I'm not going to sketch the last one. So our parent function starts at 0, 0, heads off to the right pretty flatly. It's just the square root of x. This stretch graph very sharply, much more of a curve. The last one here would just be a vertical stretch by a factor of 3. I'm not going to do that. But again, it appeared to be narrower than its point function. We're going to look at those same 3 functions, but now with different a values there. So going back to x squared, instead of saying 2x, we're going to look at 1/2 x squared. What's that going to look like in comparison? So here we see that the graph has been widened. The red lines or the red curves are further away from the y-axis than the black ones. Instead of looking at 4 times the square root of x, we're going to look at 1/4 that. Okay, so we see that the graph of the square root of x is just that flattish curve off to the right. And so 1/4, we get a much flatter curve that's really being pushed down here. And then cube, we went from x cubed to 1/3 x cubed. So there we see again that it looks wider, but the red part is further away from the y-axis than the black part. What we call this is a vertical compression. I'll talk to you guys about why that's that way, but that's what it's called. This is a vertical compression. Vertical compression by a factor of, okay. So again, our parent function should look something like this. Squared. We saw that this graph looked wider, still went through 0, 0. So this one appears wider. So if we use that same analogy, right, silly putty, right, we saw if we stretch the silly putty to the middle of the, okay, this is you guys yet? No, so if we take a piece of silly putty and we stretch it vertically, you should notice that the middle of it gets thinner, right? And so as we stretch those graphs vertically, they appear to narrow ones. Okay? Take that same piece of silly putty and instead of stretching it, we're going to take it and compress it. So what happens in the middle when you compress the silly putty? The outsides go out, right? The middle goes out now. So if we compress those y values, the graph appears to get wider on us. So why is that mathematically? So if we look back at square again, if we look at that same point, like 2, okay? 2 squared is 4. We see the point 2, 4 on the black graph. And then we take 2, we plug it in again, we get 4, but then we take half of that, right? half of x squared. So 2, or half of 4 will be 2. So we should see that point on the red graph, 2, 2. So comparing the distance from the green point, right, 4 units away from the x-axis, now to the purple point, it's only 2 units away, so it's half as far away as the green point is. Okay, so the y value has been compressed. It's half as much as it had been. So why does that make the graph look wider? So remember, these graphs grow very rapidly vertically, right? So they grow so fast vertically that we can't see much of them. Right? we just don't have much time to graph them. So what we're doing is we're slowing down that growth, which allows us more time visually to see how it expands. Right? It looks wider because we're having more time, more points available to us horizontally because the y growth is slow. And that's all visual. The math is because of the y values are being reduced. But to our eyes, it's y. Okay. We look at the square root one again. Then the number that we can square root easily will be 9. If I square root 9, I should get 3. You see that point on the black graph? I take that and I do 1/4 of that. Right, so I square root 9, I get 3, then I take 1/4 of 9, or sorry, 1/4 of 3, which is 3/4. Okay. It's a little harder to see, but again, the distance from the x-axis to the green point is 3 units. Distance from the x-axis to the purple point is 3/4 of a unit, which is 1/4 of what the green point is. Okay. So the vertical values are less than that. And because the graph just mainly grows to the right anyways, we don't really see a little bit wider for us. It just gets squished. Right? This one seems to follow the word better. It does look like a squished graph. It is much flatter than it was before. So this was vertical compression. All factor of 1/4. And then we'll see here. X should look like this. We're saying it's really squished. It's kind of a pain to draw. A really flat curve. Okay. The last one just be a vertical compression by a factor of 1/3. You guys may have heard of vertical compression as vertical shrink also. Yeah. This book uses the word compression, not shrink. It's just a different word for the same thing. So the main thing, again, this would be like our a value. You would see something y equals a times x minus h squared plus k. Or you would see y equals a square root of x minus h plus k. And this one, or you could have, for absolute value, you have a absolute value of x minus h plus k. So this would be part of our a value. A value has multiple jobs. I can also control reflections, but what we're looking at here, with that number in front of the function, it's multiplying if the absolute value of a, so we just want to look at its size, really, not if it's negative or positive, really how big the number is. If that is greater than 1, that's a vertical stretch. Okay. If the size of a is somewhere between 0 and 1, that's a vertical compression. Okay. So again, just be careful. It's not about the sign of the number. It's about the size of the number. Sign does something completely different, but you guys should remember that what the negative does. So if it's a fraction between 0 and 1, so 1/2, 0.25, or 0.7, 0.9, 7/8, those are compressions. If it's something bigger than 1, like 2, 4, 1.5, and 5/2. So there are lots of fractions and decimals that are bigger than 1. Okay, that those are stretches. That's as far as I've gotten with one of the classes, and we'll stop there.